Just a second. Yep. So, hi everyone, welcome to the tutorial on AVL Trees. And I hope that by the time we reach the end of this tutorial, you'll be quite familiar with AVL Trees and its basic operations such as search and insertions. So enjoy. So, that let me just brief you about the contents of the video. Firstly, I'll begin with introduction to BST trees and what was the need to study AVL trees. Then I'll give you a brief introduction on AVL trees and derive you the the main invariant of AVL tree, and then we'll perform insertion on the AVL tree to show how height is balanced, how height remains balanced even after insertion in AVL tree. So binary search tree. So one thing I assume here is that you all are familiar with like basic operations, like what is a binary search tree and what are basic operations like insert, delete, update. So if not, I recommend googling some good tutorial on binary search tree and making yourself familiar. To those who are familiar, they might know that all BST operations are order D, where D is the tree's depth. Like you insert, it's order D, you do a find operation, it's order D, and minimum D is log n base 2. Uh, so if you can't prove this, you can just think of contradiction. Like you assume that tree has n nodes and its height is less than this lower bound, and you you land up in the contradiction that tree doesn't have n nodes. So yes, the tree should have height log n base 2. So what is the best case tree? Best case tree is where tree is exactly having height log n base 2. What is the worst case tree? So why are they best case or worst case? You realize that every BST operation is order D. So to minimize BST operations time, you need to minimize this D. So this D in best case can be log n, in worst case can be n. So every computer scientist sought after this data structure because it offered log n time complexity for most of the BST operations. So binary search tree, worst time. Worst case running time, as I mentioned before, of a binary search tree is order n. How? What happens when you insert elements in ascending order? Insert 2, 4, 6, 8, 10, 12 into an empty BST. If you realize you are familiar with BST, what will happen is a degenerate tree as 2, right child 4, right child 6, and so on. Do the straight chain. It's not a tree, it's like a linked list in that case. We are not being able to exploit the tree structure of our data structure. And why is this? This is because of lack of balance. We are not balancing the tree. As we mentioned that the best case height is log n. So when is that achieved? When we keep our tree balanced. Balance by balance I mean that tree's height is balanced in the sense that both the left tree and the right tree have similar number of nodes. If equal, that's the best case, but similar, not very different. Their heights are very similar. Yeah. So what is a balanced and unbalanced tree? As you can see the mouse pointer in a tree of 7 nodes, this left binary search tree is a balanced tree because log n base 7 is log n base 7 is 3, and like so this tree, as you can see, is a full or complete perfect binary tree because each level is full. Like level 0 can have maximum 1 node, level 1 can have maximum 2 nodes, 3 can have level 2 can have maximum 4 nodes. Each level is full. As you can see, it's the second tree. This is known as a degenerate tree. This is formed when, like in a nave, you can see in a nave balanced BST, when you insert elements like 1, 2, 3, 4, and so on. This you can see it's not a tree structure, but it's like a linked list. So every operation in linked list is order n. So this is the trouble that this kind of degenerate tree gives. And as you can see, the third tree, is this balanced? Well, in true sense, it's not. But in some sense, it is because it's not completely unbalanced. It has some kind of balance. We don't know. It's some kind of strange balance. We'll explore it. So, what are the approaches to balancing a tree? We don't balance it. Let it end with some nodes very deep. So, what it lands up is something like the second case. Strict balance. The tree must always be balanced perfectly. So, as in the first case, it's a completely balanced tree as you insert the nodes. So this is something hard to attain because this might be not it might be not possible to attain strict balance with good complexity. So what we define is something like we negotiate between the both of the two above, and it's you can say it's pretty good balance. It's just a fancy terminology. It's but what we try like what the intuition is like you don't exactly keep the tree's height to be log n, but something of order log n. Like those who are familiar with the big O complexity notations, they realize that like n and 2n are both same. So something order log n is pretty good balance. And what the balance should be is that it should be adjusting on axis. Is that whenever the tree is built on some invariant or some property, so as soon as this property is violated on insertion or deletion, the tree is self-adjusting. The nodes realize that, oh, we are now out of the property, so we should just balance it. So now we'll directly jump to the AVL trees. AVL tree is good but not perfect balance. So as we earlier mentioned the types of balancing, pretty good balance is what AVL tree falls into, not perfect balance. That means that it offers order logarithmic height complexity but not exactly log in. But in real world, you realize that we deal with order notations and not exact notations. Yep. So AVL trees are height balanced binary search trees. Height balanced, its height is balanced. Its height doesn't randomly grow in one direction. Its height is balanced by some algorithms. Balance factor of a node, very important. Balance factor of a node is defined as height of its left subtree minus height of its right subtree. You'll like for the time being just keep it as the definition, but you'll realize that we use this balance factor to to perceive that whether the tree is now not following the property that we have defined. So we haven't defined any such property, so here's the property. An AVL tree has balance factor calculated at every node. Every node of the tree has a field in it named as balance factor, and for every node, height of left and right subtree can differ by no more than 1. That means height of its left subtree, if height of its left subtree is x, then what are the possibilities for its height of right subtree? It's x minus 1, x and x plus 1. Height of left and right subtree can differ by no more than 1. Like the mod absolute value is less than equal to 1. We store current heights in each node. So height of an AVL tree. So it is like it is quite non-intuitive, like how that balance factor, like difference of balance factor less than equal to 1 helps helps us keep the height to logarithmic. So here's quite a rigor mathematic proof. If you are not quite good at recurrence solving and others, you can just skip 2 3 slides to the other part of the lecture. So what is like we define a recurrence to show that a tree with height h in AVL tree will have 5 to the power h nodes. Yep. So like let's go forward. So n of h is defined as minimum number of nodes in an AVL tree of height h. The minimum word is important. N of h is minimum number of nodes. So what are the base cases? When a tree is of height 0, there are one node, the root. As you can see, in one node there is no root or something. When tree has height 1, it has two nodes. So like a tree with height 1 can have 3 nodes as well as 2 nodes, a root with 2 child or 1 child. So minimum number of nodes will be a tree with children, 2 child, two nodes. Yep. So and the induction case is number of No, minimum number of nodes in a tree of height h is minimum number of nodes in a tree of height h minus 1 plus minimum number of nodes in tree of height h minus 2 plus 1. So let's break this three terms down. This plus 1 is let me begin. This plus 1 is for the root. So when once the root is taken off, as you can see in the right part of the diagram, as the root goes, we will be left with two subtrees. So the one subtree has height h minus 1, other has other side is mentioned h minus 2. Both, there is reason for both of them. Firstly, you need to realize that one of the subtree will have height h minus 1. That's for sure. Like any of the two can have height h minus 1, because let's assume that none of them has height h minus 1. That means each of them has height less than equal to h minus 2, and in that case our tree will be having height h minus 1. So at least one of them has height h minus 1, and greater than h minus 1 is not possible, otherwise the tree will have height greater than h. Yep. So at least one has height h minus 1. Now n of h is minimum number of nodes in an AVL tree of height h. So as we mentioned before, if if a left subtree of tree has x number of nodes, the possible candidates for the height of right subtree is x plus 1, x and x minus 1. X plus 1 can't be, because then the right subtree will have height h, and in that case tree will be having height h plus 1. The other two candidates are h minus 1 and h minus 2. So one trivial fact that I am not proving here is that this n of h is an increasing function of h. Like if you increase height of the tree, minimum number of nodes that the tree will AVL tree will have is also increasing. I am not proving it, but you can again prove it by induction. So if we do h minus n of h minus 1 is greater than equal to n of h minus 2, to find minimum of n of h, we take n of h minus 2. Others are not possible because it's an AVL tree, so the property of AVL tree will be violated. Solution to such a recurrence is n of h is greater than equal to 5 to the power h. 5 is equal to 1.62. Let's see how it comes. Key idea is, like from the previous slide we saw that this was the recurrence. So if we remove this plus 1 to make this recurrence simple, we see that n of h is greater than equal to n of h minus 1 plus n of h minus 2. So if we assume that n of h is of the form t to the power h and substitute back in this recurrence, we get t square is greater than equal to t plus 1. Solution to such a recurrence is n of h is equal to a times 2 to the power h. A is a parameter found using base cases. We had two bases, as you can see in this slide. Yeah. So what we saw is that height of an AVL tree n of h is greater than equal to 5 to the power h. The minimum number of nodes in a tree with height h is greater than equal to 5 to the power h. So suppose we have an n nodes in an AVL tree of height h. What we know is that this n is greater than equal to n of h, because this was the minimum number of nodes for height h. So n is greater than equal to 5 to the h. Hence log n base 5 is less than equal to h. What we see is that our height of AVL tree on n nodes is less than equal to 1.44 times log n base 2. This 1.44 is immaterial. What we actually attain, or what this AVL tree has beautifully achieved, is that it has been able to keep height of the tree for n nodes to be order log n. If you realize it's order log n. So just go through the proof once again if you're in a doubt, and you should move forward. So this is a simple example of AVL tree. Node heights. How do we enumerate nodes and balance factor? So let's see the left tree and see whether it's an AVL tree or not. So let's see first the leaves. Leaves are 1, 5 and 9. Each of these has been labeled 0. First, some convention. Height of node is h. Balance factor is height of left subtree minus height of right subtree, and empty height is minus 1. Just a notation. So leaf has height 0. If we calculate height of node 4 in the left subtree, it's maximum of height of left subtree comma right subtree plus 1. So maximum of 0 comma 0 plus 1, it's 1. Similarly, this is 2. So balance factor at each node, at this node it's 0, at this node it's 1. So this tree satisfied the AVL tree property. Similarly, you can check for the right node. I am not doing it. What happens when we insert 7? So left tree will still remain an AVL tree. I'm not going through it, but let's see right subtree, right tree. As you can see, it will not be an AVL tree. As it like just not going into the mathematics, but from the visual, you can realize that some kind of disbalance has already occurred. So let's study. What are the new leaves? Leaves are 1, 5, 7. Each of them has height 0. Height of 8, height of 8, node 8 is 1. Height of node 9 is 2. So if we study balance factor at node 9, height of left subtree is 1. Height of right subtree is minus 1 because there is nothing. So empty height is minus 1 as we have mentioned below. So balance factor of 2 is a clear violation to the AVL tree property. As we mentioned that balance factor has to be between minus 1 and 1. Minus 1, 0 and 1. These are the only possible values that balance factor can attain at any instant of AVL tree if it's an AVL tree. So what was the problem? When we performed insertion in an AVL tree, we realized that its invariant got disturbed. So we come up with needs that we need to develop algorithms to maintain invariant of the AVL tree. By just maintaining the invariant about the balance factor, our mathematics says that its height will be log n. So we as computer scientists guarantees its balance factor to be between minus 1 and 1, and mathematics guarantees us that the height will be log n. So as we proceed further, it's written clearly that insert operation may cause balance factor to become 2 or minus 2 for some node. You will realize that it can't be 3 or minus 3 because when the tree is balanced it's 1 or minus 1. So inserting a node will just make one part of the tree's height increase, so it will be always 2 or minus 2. It's a continuous function, so it's actually we should not think about functions, but it's a trivial fact. Yeah, only nodes on the path from insertion point to root node have possibly changed in height. That's the argument why it will be 2 or minus 2, no other number, if at all, if they get disbalanced. So after the insert, we should go back up to the root node by node, updating heights. If a new balance factor, that is the difference between the height of the left subtree and the right subtree, is 2 or minus 2, we adjust the tree by rotation around the node. So all these are the abstract level of the algorithm. We'll soon dive into it. So this is an example. So this was the subtree that we picked last time. So we inserted 7 and we realized that node 9 there is a disturbance in the balance factor because the left subtree has height 1 and the right subtree has height minus 1. So when we insert 7, so it goes down in this path 6, 9, 8 and insert 7 to its left. And when it backtracks, it checks at 8 whether balance factor is still maintained or not. As it is maintained, it again backtracks and reaches 9. And it realizes that it is the invariant has got disturbed. So what it will do is rotation. As you can see the arrow, this is the new rotated balance tree. So what has happened is that this 8 node that was here has rotated up and become the root of the right subtree of 6. 9 has gone to its right and 7 remains the left child of 8. So as you can see that AVL tree, firstly this is the BST binary search tree properties are maintained. Secondly, it has become AVL tree. AVL tree because the violation at node 9 is now balance factor 0, 7 is also 0 and 8 becomes balance factor 1. Initially its balance factor was 1, now its balance factor has become 0. So we see that and from node 6 to others it's all balanced. So we clearly see that all the balance factors are maintained. So this becomes an AVL tree. Just a single rotation. So insertions in AVL tree. Let the node that needs rebalancing be alpha. You can call it anything. So there are 4 cases. Outside cases. It requires single rotation, insertion into the left subtree of the left child, insertion into the right subtree of the right child, insertion into the right subtree of the left child, and insertion into the left subtree of the right child. let's go back to the previous slide and see what happened is that it was like insertion into the left subtree of the left child. 7 is the left child of 8 and 8 is in the right subtree of 9. The disturbance node is alpha. So 8 is the left subtree of 9 and 7 is the left child of 8. Similarly, you can think that right subtree of right child is a symmetric case, and the other two inside cases are more non-trivial and complex to deal with. We'll study all four of them. So AVL insertion outside case, like insertion into the left subtree of the left child or right subtree of the right child. So as you can see, we have considered a valid AVL tree of height h plus 2 because subtree x, y and z each has height h, and so the height of node k is h plus 1. Node of height of node j is maximum of h plus 1 comma h, that is h plus 1 plus 1, h plus 2. So balance factor at node k is 0, balance factor at node j is 1. So it maintains the AVL tree, and x, y, z are clearly like they all satisfy AVL tree property. We assume this. It's a valid tree. So AVL insertion outside case, like insertion happens, like if a node is disturbed, then insertion had happened in the left subtree of the left child or right subtree of the right child. So these are the two cases. As you can realize, insertion into the left subtree of left child or right subtree of the right child. Yeah. So inserting into X destroys the AVL tree property at node J. So let's assume that a node came into the BST here and it got inserted through J, K into the X, and in such a way that height of the subtree X increased by 1. What this causes is that height of node K becomes h plus 2, height of node J becomes h plus 3. So if we calculate balance factor at node K, it's h plus 1 minus h, which is equal to 1. No problem. But if we calculate balance factor at node j, it's h plus 2 now. And right subtree is h, which is equal to 2. So this is causing an alarm for the invariant of the AVL tree that now you are getting destroyed. So if you want to keep height to log in, you need to self-adjust yourself. You need to think intelligently. So immediately AVL tree comes up with the response that J will send signal to its left subtree K that you have gone out of order. So now you need some kind of algorithm for this. You should now balance yourself as you are becoming too heavy. Your height is becoming too large. So immediately K comes up to the rescue to decrease its height. So what you can see is that some kind of a right rotation, a clockwise rotation is happening, in which the heavier or the taller part of the tree is trying to decrease its height, and the right part of the tree, which is shorter, is gaining height. So as we realize that this rotation is what is balancing the tree, balance in the sense that both the left and the right subtree of the root has equal height, and maybe similar height is better to say. So as k tries to rotate, we see that K's link with J and K's link with Y are broken, as K will become the candidate for the new node of the tree. And we join this Y subtree with J because Y, all the elements in Y are less than J and they are greater than K. So we can safely join this link. And because K has become the new subtree, new root of the tree, J needs to be joined as a child of K and inherit this. Right rotation done. K becomes the new root, J becomes the right child of K, and Y is joined as a left subtree of J. So if you now calculate balance factor at each node that were disturbed, you realize that at node J, both the trees have height h now, so balance factor is 0. And at node K, one has height h plus 1, the other also has height h plus 1. So this again becomes 0. So this is quite good because you see that initially, tree had become momentarily of height h plus 3 here. If I am correct, it becomes of height h plus 3, h plus 2, h plus 3. And this, so the intuition says that whenever AVL tree height becomes some like exceeds some threshold, the tree is sent some kind of a alarm that now your height is increasing too much as compared to the nodes you have. So you have capacity to balance yourself and decrease your height. So immediately AVL tree sends a response to its children all over the tree that do corrections as earlier instructed. So they do corrections and this balances the tree. So left rotation is exactly the mirror symmetric case of the right rotation. So this is being left as homework. AVL tree insertion inside case. So I recommend that you should be a little more focused for this part because this is not little involved. Consider a valid AVL tree. Again, this is valid. So height h plus 1, balance factor 1 at node j. It's valid. So here AVL insertion happens through the path j, k and into the subtree y in such a way that height of subtree has increased by 1. So inserting into y destroys the AVL tree property at node j. As you can see, height of k is become h plus 2, height of this right subtree is h. So balance factor at node j is 2. So does right rotation restore balance? Let's check it out. Maybe it's if it restores balance, then we are done. Like this one algorithm is sufficient. We don't need to worry a lot about the tree. But let's do a right rotation. Like in this right rotation, k will become the new root of the tree, and this y will go to j. And let's see. This is the right rotation that we studied. So what does this right rotation do? K becomes a new root, and y is attached to j. But does this restore balance now? Let's look at node J, the popular, like the most popular problematic node. So at node J, it's balanced because left subtree has height h plus 1, right has height h. The difference is 1. But what about node K now? Initially J was disbalanced and K was balanced. But what about node K now? K's left subtree has height h, right subtree has height h plus 2. Balance factor is h minus h plus 2, minus 2. Again, alarm to the tree that your rotation has not balanced me. The rotation algorithm has not balanced me, so my height might explode. So you need to take steps to balance it. So what to do now? So this was the initial structure that happened when the tree insertion happened in the right subtree of the left child of the disturbance node. J is the disturbance node. So insertion happened in the left child's right subtree. Y. So Y. So we can think of Y as a subtree. So it is made of a node I and two subtrees V and W. So why do we know that this node I exists? Because this tree can't be totally empty because we recently inserted a node. So V and W might be empty, but there has to exist an I. Just think about it a bit. If it's going above, just think. So as height of subtree rooted at I is h plus 1. So again with the argument given before, one of the tree has to have height h and the other will have height h minus 1. Like any order can be true for this because insertion have happened in this tree. So what about rotation now? What we do is something known as double rotation. We initially rotate the tree making k as the root. Initially rotate the tree so that I becomes the root of the left subtree of j, and this part gets a little balanced. As you can see the mouse cursor, this part will be balanced first. I will go to this part, k will become the left subtree of I, and then again we rotate making I as the new root. So let's proceed. This is the first rotation. A left rotation because a left rotation a left rotation does what it does is that makes the I as the root, k becomes the left child. But does it solve the problem? No, because still x has height h. So w and x both had height h, as I am sure, as I was, yeah, x and w both has height h. So k has height h plus 1 and I has height h plus 2. So what happened? The difference is 2. Balance factor 2. Still not balanced. What can we do now? We can now This balancing is showing that this part, the left subtree of j, is quite a bit heavier in height or in weight as you interpret. So why not do a right rotation now? So let's do a right rotation and see if it improves the situation. So now do a right rotation. And yes, like before going into the diagram and balance factor, we can visualize and see that now the tree is looking quite balanced. So as we go into the depth, we see z as height h, w as height h or h minus 1. So j is balance factor is 1 or 0, whatever the case is. Similarly for node k, it will be 1 or 0. And node I, height can be height of node k is h plus 1 because x has height h. Similarly for j, so the balance factor of node I has now become 0. So in this way, and individually initially x, v, w and z all were balanced. So this two rotations, the double rotation or the second rotation in double rotation, balances the height and completes the invariant of AVL tree. So balance has been restored. So how about implementation of an AVL tree? AVL tree, each node stores four major properties. First is the height, the most important property that keeps track of its height growth and prunes it, or not prune it, but it balances it for while insertion or deletion. Key is the object that you store in the node. Left and right pointers to the children node of the node. So these the key and left and right are standard of BST, but the new part is the height. No need to keep height, just the difference in height, that is the balance factor, has to be stored. So this is a little more involved implementation of AVL tree, which can be avoided at this stage if you are a beginner. But if you are quite familiar with AVL trees by now, then you realize that we actually don't need to store heights, but we can work with balance factors. And can you think of an advantage of using only balance factor instead of heights? Yes. So if you can't, so you realize that height can be order log n in an AVL tree. So if a tree has node n, this height field needs to, like, height field has to store values up to log n, order log n, but up to log n. So it will require log of log n bits. So you realize, actually this is quite an involved conversation. You can skip to the next slide if you don't want to, but if you are quite memory efficient, then you realize that in a node in an AVL tree is occupying space proportional to log of log n. In practice, log of log n is quite a small number, but if you are in a memory constrained space, then this log of log n can also come quite handy. So storing balance factor is like you are storing a bit, 1 or 0 or minus 1. Like you can keep it with very low, it because balance factor is independent of n. It can be minus 1, 0 or 1, 2 or minus 2, not further. So keeping balance factor is quite a safe and quite memory efficient manner. But again, all the insertion algorithms become quite little involved and trickier. Not that it can't be done, but for a beginner it's quite trickier. So once you performed a rotation, single or double, you won't need to go back up to the tree. So these are just simple implementations of what we discussed right now. Rotate from right receives a pointer. You also need to modify the heights of balance factor of n and p. So this you can do. This is quite simple mathematics and nothing else. It's not computer science, it's mathematics. So p is a node pointer type declaration. So initially we declared its type. Now we are assigning it to the right child of n. Right child of n is given. N dot right child is p dot left child. N's right child is now p's left child. So p is node pointer. So you can just go through the code. Like it's quite simple C code. And actually not C code. It's just a template of the code. So it's not a point going through it. Or maybe I can just brief you, like n is the problem node. So we need to rotate it left and bring this n's right child to the root. So n is the pointer received in the function. N's right child is stored in p. and n's right child is now assigned p's left child, because when we rotate it, y will go to the left, like become the right child of the initial root, and p's left child, the pointer's left child, will be equal to n. So as you realize that when this becomes the root, this the initial root will become its left child, and then assign the new root as the right subtree. So this balances the height. Just try to draw it on paper, and you'll realize writing the heights that this is the correct algorithm. Insertion in AVL trees. Insert at the leaf. As for all BST, only nodes. So this we have discussed earlier. This is just a recap. Only nodes on the path from insertion point to the root node have possibly changed in height. After the insert, go back up to that root node by node, updating heights. And if a new balance factor, the difference in h height of left subtree and right subtree is 2 or minus 2, adjust tree by rotation around the node. So these are the key steps in of the algorithm. To insert in AVL tree, examples of insertion in AVL tree. Insert 5 and 40. So when you insert 5, you realize that you traverse 20 down 10 down 5. So 5 got inserted. Now you insert 45, it's 20, 30, 35, 40, 45. 45 makes the tree unbalanced. You can realize that it's unbalanced. Like initially it was balanced, 1, height 2. So balance factor is 1. Balance factor is again 1. So it's maintained. But here you can see that the right part of right subtree has become quite degenerate kind. Like it's a long length list. So just perform a rotation at 35, because balance factor here is 1 minus 1 minus 1 minus 1 minus 1, which is equal to minus 2. Again a violation at node 35. So we perform a left rotation, because it's case where that 45 is in the right subtree of the right child. Right child is 40, right subtree is of 40 is 45. So perform a rotation at 35, and you can see in the right part it's balanced. Now insertion of 34 causes a disturbance in the left subtree, of the right child of 30. Right child is 40 and left subtree is 35 and 34, this tree. So this node is disturbed. So what we do, what if you remember the steps, we will try to balance the right subtree first. So how can we do that? Just rotate 35. So if so, this is a final answer that you will get after two rotations. You can just work it out. The initial rotation will be bringing 35 to the root, and 40 becomes the right child of 35, and 34 becomes the left child, and then bringing 35 back to this left, becoming the root of this right subtree of 20, and 30 will become its left child. So this is double rotation solution. Double rotate from right is rotate from left and rotate from right. So you can just work it out. In this case, double rotation can be there's a brief note, can be avoided, making whole process efficient. But the same is ignored to keep things neat and simple. So I'll not discuss this, but what we are doing in this inside case is that we are doing double rotation. So you can realize that each rotation we are assuming constant time, but it's quite a fair bit of exchange of pointers, like 5 to 6 operations. So what we can do is we can directly manipulate pointer in single rotation so that they are in the correct position, maintaining the balance factor. But we have avoided it because again it becomes quite little tricky and involved. So just a note, here we have not shown update. We have not shown update of heights, as it's quite a simple mathematics. You can just work it out on paper, make a function, get height, and you'll realize how easy it is to manipulate it. So a word about deletion. Deletion is very similar to insertion, so its discussion is omitted. The main problem is deleting a node with two children. So when you study deletion further, maybe in my next video, you realize that deletion is quite similar. In fact, if you understand insertion, you can try figuring out deletion yourself. Just remember the traversals and like the next candidate possibly, and you'll try to figure out. But the main problem is when you delete a node with two children. When you delete a node with one children, you can simply put the subtree left or right, whatever, and attach it to the parent of the deleted node. But when there are two children, then you are in a fix because you don't know which subtree to promote or which subtree to like which subtree will go in which nodes children. So, and one more caution is that deleting causes imbalance. So you should always remember to balance the tree. So what are the pros and cons of this beautiful data structure? So what are the pros? Search is order login. We didn't discuss search because search is very trivial in binary search trees. So every binary search tree supports search in order height of the tree. So here height of tree is login. Insertion and deletions are also login. We discussed insertion in quite a detail. Deletion is left as a homework for the viewer. Height balancing adds no more than a constant factor to the speed of insertion. So we mentioned that this height balancing, or also known as rotation, is taken as a constant time because it's just 3 to 4 pointer exchanges. So what are the argument against using AVL trees? It's difficult to program and debug, more space for balance factor. So definitely it's difficult to program and debug, and more space. Actually balance factor takes quite a low space, but it's still a little more than red black trees, another of one of the competitors of AVL trees, which does it with just a single bit indicating whether a node is red or black. Asymptotically, they are faster, but rebalancing costs time. So one thing you'll realize when you grow with experience in data structure field is that AVL trees are strictly balanced binary search trees. So I'm not going to throw light on this term, strictly balanced or loosely balanced, but you'll realize that when you study AVL trees and red black trees, that red black trees are loosely balanced, so they take less time in balancing. Most large searches are done in database systems on disk and use other data structures. So this clearly fails. AVL trees clearly fail when it comes to loading data from memory. Memory in sense secondary memory. So whenever data can be totally fitted in primary memory, or what you call as random access memory, RAMs, then AVL trees work fine with order login. But if it has to be in real time loaded from a disk, then you should try using some other trees such as B trees. And it's maybe okay to have order n for a single operation if total runtime for many consecutive operation is fast. So just skip this last part because it's little involved. So yeah. Thank you for watching this video and being patient. And if you think you have questions that I have been unable to make clear, just comment it below and you'll get your response as soon as possible. Thank you.